Hello and welcome to this vodcast 1.2b propagating errors. So in the previous vodcast we had looked at what random and systematic errors are, and now we're going to move forward in actually looking at some of the consequences of those errors, covering quite a large part of the topic, and also we're going to be using those equations from the data booklet and explaining what they mean. We'll start off by just examining the different types of uncertainty that you can get. This one we've met already, the absolute uncertainty. So the absolute uncertainty is always an uncertainty that's quoted in the same units as the measurement that we're making. So for example, if we're measuring a length, we might say the length is 2.0 centimeters plus minus 0.2 centimeters. So that gives you the potential uncertainty within that measurement, or our best estimate of the potential uncertainty. The fractional uncertainty is found by taking that uncertainty, the absolute uncertainty, and dividing it by the measurement. So what fraction of the measurement is the uncertainty? It's not got a unit because it is a ratio. The other way of thinking of that is as a percentage. That's what the way you normally sort of think about these things in your head, is as a percentage, and indeed write them down. Fractional uncertainties are used in calculations. Percentage uncertainties are sort of how you write down fractional uncertainties normally, but even percentage uncertainties would be rarely, if ever, quoted in an actual lab report. In a lab report, you would almost always just stick with the absolute uncertainties. So propagating errors comes about because whenever we make a measurement in physics, we're often needing to combine that measurement in order to determine something from that in the processed data. Okay. So, for example, you might need to calculate a force, which you would do from calculating something's mass and its acceleration. And its acceleration itself is often not something you would measure directly, but instead you would measure changing velocity over time, both of which would have their own uncertainties. And any uncertainties in your input data will lead to uncertainties in your final outputs, in the output. So let's look at some examples. So one potential calculation that you could do is you could calculate the perimeter of one of the squares that make up the side of our die. And that's an example of just adding together several measurements, each of which have their own uncertainty. In order to add together measurements, they basically have to have the same unit. So lengths might add together, times might add together, etc. So P equals x plus x plus x plus x plus x, 4 x's. Each x is 2 centimeters plus minus 0.2. So your final result is 8 centimeters plus minus the uncertainty. How do we calculate that? Well, that's where we use this equation. If the result is just previous calculations added together, a plus b plus c plus d, etc., or minus, then the uncertainty in the final result is the uncertainty in the a and the uncertainty in b. Now, all our measurements were the same, so our uncertainty was plus minus 0.8 centimeters. That's not too surprising, that's fairly obvious. What maybe is not so obvious is the fact that that also works for subtraction as well. Even if you're subtracting the values, you add the uncertainties. If adding or subtracting measurements, add the uncertainties. Another function we could find is the volume. The volume is one side cubed, which is x times x times x. So we're no longer adding, we're now multiplying. X is still our original measurement. V is 3 times that, x times x times that, is that cubed, sorry, and 2 cubed is 8, plus minus, well, you add the fractional uncertainties. That's what all this equation means. If you're multiplying or dividing to find a final answer, you always add the fractional uncertainties. Uncertainties. So 0.1 fractional uncertainty, 3 times gives you 10%, so to speak, which will give you 0.1 plus 0.1 plus 0.1, okay, which is 0.3. Again, you add the fractional uncertainty, and the fraction 0.3 of 8 is 30%, which is 2.4 centimetre cubed. So again, just to go through that again, you're actually doing the fractional uncertainty, but it's easier, at least for me, to write that down as a percentage and then convert it into a absolute uncertainty. And like all absolute uncertainties, we can only quote it to a maximum of 2 significant figures. If multiplying or dividing measurements, then add the percentage uncertainties. Seems to be the basic rule there. This equation does feature in the data booklet, although I find it only very rarely to be used. If you have a value to the power, then that power multiplies by the uncertainty in your value to give you the fractional uncertainty in the final result. So v equals x cubed, for example, then the uncertainty in volume is 3 times the uncertainty, the fractional uncertainty in each length. Each gives you 0.3, which is 30%, which is still 2.4 centimeters cubed. Let's look at that actually being applied to a result. Okay, so here is the pendulum data from the previous lab. We calculated the average for 5 swings, but suppose we want to calculate the actual average for 1 swing. Well, we calculate the fractional uncertainty, or the percentage uncertainty if you prefer, 16.1%, 7.2%, etc. If it was 5 swings, we divided through by 5 to give us the period, the 1 swing period. And now 5 itself is just a number, it doesn't have an uncertainty. So the fractional uncertainty stays the same, the percentage uncertainty, which we convert that back into an absolute uncertainty and gives us our reviewed and revised absolute uncertainties for 1 swing period rather than 5 swings period. By the way, also it's worthwhile adding 0, 0, 0 as a line in our data table, which we can infer because in this case, when length is 0, the period would be 0. We'll be using that in the next podcast. Thank you very, very much.